is mechanical vibrations. And we're going to talk about a few different aspects of mechanical vibrations. But I'm going to first start with just a simple harmonic oscillator. So we're just starting with a harmonic oscillator, which is a spring and a mass oscillating. And we're going to start out with an undamped case. And so that's a system that looks like this. You have this mass that moves frictionlessly across this surface, and it's connected to a spring, and the spring has a constant K. And if you pull this thing back or push it in and then release it, it'll oscillate back and forth. Okay, there's no friction or anything, so this way of modeling this system, it'll just keep oscillating back and forth forever, okay, with sinusoidal shaped curves over time. And then the second thing we're going to get into is damped oscillation. The damping that we're going to use is viscous damping. So you can imagine we could use dry friction to provide damping, but we're going to have damping that's proportional to the speed the thing's moving. That's what like a lubricant-filled damper would do. And so this will be represented by something like this. You have the same mass M. And you have a spring K. And then in addition to that, you have, this is how people represent this damping. And it has a damping coefficient C. Okay. And for damped, there are a few different cases. The math breaks down into kind of 3 different directions. And I'm going to drive all this. First is the overdamped case. And these all have precise mathematical meanings, so you don't want to talk loosely about this. These mean mathematical things that we'll go into. And the overdamped case, so the oscillation that would occur, the oscillation dies so quickly that it takes a long time to return to the equilibrium position. The second case, usually in control systems, this is the case that you're looking for, is called critically damped. The damping is less, and this is the fastest return to equilibrium. So you can imagine if like shocks in your car or whatever are oscillators, you want to design shocks so they return to equilibrium right away. You don't want to define them so you bounce up and down the road, Yes?
Is there one critically damped case, or can it be critically damped over a range of values of K and C?
There's only one critically damped case. So usually, like if you're designing the system, you want your K, M, and C to be such that that you achieve this. And then the last one is underdamped. And it's not particularly useful as something you're trying to achieve, but this is the one that's the most interesting mathematically. And it's going to bring up something that's such an important relationship in applied math. This is the one that shows the relationship between complex exponentials and cosine and sine. Have you ever seen that in a class before? I guess if you've taken differential equations, maybe you've seen this. But it's just the coolest thing in the world, and it always, in some way, involves Euler's formula, which says e to the ix, where x can be anything. Actually, let me write it like this. So b is just like some constant, some number, whatever. This is equal to the cosine of b plus I times the sine of b. It's the kookiest, wackiest thing, and it's super, super useful, especially in control systems and electrical engineering, but we're going to see it here in oscillating systems.
That's definitely top 4.
Okay, yeah. Okay, so we're going to start out easy with the undamped case. Maybe you've seen a quick derivation of this in Physics 1, depending on who your teacher is. And then we'll get into this stuff that you probably didn't see in Physics 1. The people who are taking deform right now, it's going to look so similar because the governing differential equation is basically the same.
Yeah.
Okay, so let's do the undamped case. So an undamped harmonic oscillator. So you have this cart with a massive M, and you have a spring with a spring constant K. And we want to figure out what the motion of this is going to look like. If you draw a free body diagram of the cart, you have a weight force down of mg, a normal force, and then the force from the spring, if you draw your arrow in the positive x direction, that force is going to have the magnitude negative kx. I also could have drawn the arrow in the negative x direction and labeled it as kx. It's the same thing, but I put the negative in there because you often see that formula for the force, that the force applied by a spring is equal to negative kx.
So in this case, the spring is pushing the cart away from the wall?
When it's in equilibrium, x is equal to 0. Okay, so if x is positive, then, like you said, the card is over here, then the force is in the negative direction, so it's pushing it. If you stretch this back, x is negative, okay? You put a negative in there, and that says that it's in tension, okay? So that force always accounts for which way it's going, okay? So if x is less than 0, the spring pulls this way, and if x is greater than 0, the spring pushes this way. Okay? So let's go to Newton's second law. We have the free body diagram. So Newton's second law says, I'm going to first do it all as a vector thing, and then we'll see what's useful. So 0, negative mg, plus 0n, plus negative kx 0 is equal to the mass times the acceleration. And the acceleration is only in the x direction, so I'll write it like this. Okay, so our x component of this equation says negative kx is equal to ma. Well, a is the second time derivative of x, so now we can write this as negative kx is equal to mx double dot. And then move these over to the same side, divide by m, and you come up with this equation that says x double dot plus k over m is equal to 0. So this is the governing differential equation. It's an ordinary differential equation because the only independent variable is time for undamped harmonic motion.
You're missing a factor of x in the sentence.
Yes. I did that in D form too. I get so excited about the k over m. Okay, so there's the governing ordinary differential equation for undamped harmonic motion. So what's a solution for that? Well, the people in D form have already seen this equation, and you know that both sine and cosine work for this. Makes sense. There are two possible solutions. One is cosine and one is sine, you know, so x is equal to cosine of. So if you need the second, so we need x double prime to be equal to negative kx over m. Okay, and so when you take the second derivative of a cosine function, you get a negative cosine function, right? So that takes care of the sine of it. And then what about the argument in front? Well, notice if your argument is square root of k over m times t, if we take the first derivative of that, we get negative square root of k over m times sine of that same argument. Take the second time derivative, and you get negative k over m times the cosine of that argument. Okay? And so negative k over m cosine plus k over m times cosine is equal to 0, so that works. And sine does the same thing. So if x is equal to sine of square root of k over m t, x dot is equal to positive square root of k over m cosine square root of k over m times t. And x double dot is negative k over m sine square root of k over m t. Okay? Both of those work, so we're going to make a general solution for this, a solution that encapsulates every possible solution to this. The general solution is x is equal to some constant c1 times the cosine of square root of k over m t plus c2 times the sine of the square root of k over m times t. Okay, that's before the boundary conditions. Okay, so now let's, so now we're going to go from this general solution and we're going to decide what's happening at the time equals 0 or whatever. Just give some relationship between the position and the time. And we can use that to find these constants C1 and C2. So now we're going to use the boundary conditions. And I'm going to say that when x is equal to 0, when time is equal to 0, sorry, x is equal to positive L. Okay, so what we're saying is we're pushing this thing in a distance L and then letting it go from rest. And if we're letting it go from rest, we also know that x dot at time equals 0 is equal to 0. Okay, so I'm going to start with this one. X dot at time equals 0 is equal to 0. Since we know that x has this form, we can just take the time derivative. So we have negative c1 times square root of k over m times the sine of, if you plug 0 in for time, you get 0 for the whole argument. Just plug 0 into the argument of the cosine and the sine. And for the second term, the derivative is c2 times square root of k over m times cosine of 0.
Question.
Yes.
The boundary conditions from the third one, is it supposed to be x double dot?
There's only 2 of them, and I listed out I just need more space here.
Okay, sorry.
So those are the,
Okay.
those are the only 2, and I'm just going through them to come up with these constants. Okay, and we know that x dot, when we plug in 0 for time, is 0. So this has to be true. Sine of 0 is 0. So we lose any information about that one. But the only way that you can make, cosine of 0 is 1. So this says that C2 times square root of k over m is 0. Square root of k over m can't be 0, so C2 has to be equal to 0. Okay. And so now I'm going to update my expression for the position as a function of time. And this is equal to C1 times the cosine of the square root of k over m times t. The second term went away. And now I'll use the second boundary condition that says x when time is equal to 0 is equal to 0. Okay. And so x when time is equal to 0 is C1, this is wrong, sorry. Our other condition said that when time is equal to 0, the position is L, right? If the position was 0 and the velocity was 0, then the thing is just going to be sitting there. Okay, so you have to stretch or compress the spring a little bit, and we compressed it to L. So x at time equals 0 is C1 times the cosine of 0, and that has to be equal to L. And so C1 is equal to L. And so our final update says x as a function of time is equal to L times the cosine of square root of k over m times time. So this is the solution for an undamped harmonic oscillator that's released from rest at position x equals L. Okay, and this one by itself tells us everything that we're going to need. So now let's figure out a little bit about like how fast this thing is going to oscillate, that kind of thing. So now we're going to use this solution that we just came up with to find the period. That's the elapsed time that it takes for this thing to repeat itself. So this is the time required for one entire cycle. Okay, how do you think we're going to find the period for this? Well, think about what the period is for cosine or sine. They repeat every 2 pi, right? So we know that the argument for this cosine needs to be equal to 2 pi for one period. Okay, so cosine repeats every 2 pi. And so we're going to say that the argument of the cosine function times some value t is equal to 2 pi. And then we just have to solve for that t. Okay, so T, which we're going to call the period tau, that's just what people usually do, is equal to 2 pi times square root of m over k okay? Now, if instead of the period, so if something's oscillating faster, is the period bigger or smaller?
Stronger.
Yeah, that's right. The period gets smaller. Anybody remember the relationship between period and frequency?
Reciprocals.
Yep, they're reciprocals. So the frequency f is just 1 over the period. And so that's equal to 1 over 2 pi times square root of k over m. And this is called the natural frequency of the system. And it's called the natural frequency because you could put a powerful motor on this thing and make it oscillate at a different frequency if you wanted. But once you stopped forcing it, stopped applying that external load to it, it would go back to this frequency. Okay, so this is the system's natural frequency. An important thing about the natural frequency is if you're applying forces to something that matches the natural frequency of the system, that's when you get increasing magnitudes of, increasing amplitude of this system. So like, if you've ever seen the video of the Tacoma Narrows Bridge, what's happening is the wind is in some way causing a forcing function that just happens to match that natural frequency, and so the amplitudes increase and it eventually breaks. Okay, so let's graph this. So this is the position, and it looks something like that. This distance and this distance are both L. The cycle repeats itself here. And so the time value, and it also repeats itself here. So this time value is 1 period. And so that's equal to 2 pi times square root of m over k. And then if you go to the next one, this is just another one of these. So 4 pi times square root of m over k. Okay? So what does this say? How would you make these oscillations faster? There are 2 ways you can do that. And this graph tells you how to do that. You can decrease m, because that reduces the period, and or you can increase k. Okay, so for faster oscillations, you can decrease m or increase k. And then, question?
Pocket watch. Like, do they have like the spinning wheel?
Yeah.
And they would time it by, you can make adjustments on.
Yeah, exactly. Well, that's a torsional spring, but we'll we'll talk about how to calculate stuff for torsional springs too. But this also works for pendulums, and that's how they do it for grandfather clocks.
Yeah.
Nothing's cooler than old pocket watches and old grandfather clocks. Like, I think I'm going to talk about that later on, so I'm not going to get into it now. But basically, like, you have all your power in like a spring, a big spring, and then you have this little spring over here that just beats out its little rhythm, and you have that calibrated to a really precise frequency.
Yeah.
Okay. But the problem is if you move the little precise spring, it'll oscillate a couple times and then die down. So that won't work. You can't be messing with your pocket watch every 2 seconds to have it keep time. And this one over here has a lot of power in it, but it doesn't know anything about time. It's just going to let all its power out. And so they have this amazing little contraption in between, a little fork thing, that when the timing mechanism is one way, it stops the release of the power. And when the timing mechanism swings the other way, the power comes through and gives the timing mechanism another bump. So it works like both ways. The little thing regulates how power is let out of this thing, and the power in this thing continually bumps it's amazing. And I know I've said this many times in many different contexts, but the advent of like digital electronics ruined a lot of cool engineering. There was so much like ingenious engineering that went on that digital just came in and worked better for everything and worked the same for everything. And so, all these old ideas kind of became, obsolete, but there's some really cool stuff from the old days.
People still like pocket watches.
Yeah, I always wear watches with mechanical movements because I just think it's the coolest thing in the world, Yeah. It's not nearly as accurate and whatever, but it is cool. Okay. And then, so that means that for slower oscillations, you do the opposite of this. So you can increase M or decrease K. Okay, I'm going to do an example. And in this example, I'm going to orient the spring vertically. So there's no wheels or anything. I'm going to say this is 1.5 kilograms. And I'm going to say that when so we're going to start without knowing the spring constant, okay? And I'm going to say that when you release this mass or, let it hang down to equilibrium, the spring stretches 3 centimeters from its resting length. So 0.03 meters from its resting length. Okay, well, we don't have the K value, but we can use this to calculate K. And let's say we want to calculate the frequency of this system, the natural frequency, let's say. Okay, so let's first figure out what the K value is. So I'm going to draw a free body diagram of the system. We have a weight force down that's equal to 1.5 times 9.81, so 14.715. And then we have a force up that's equal to 0.03 K. Okay, that's the negative Kx. I just did the direction for us. And so Newton's second law, just looking at the y component, says 0.03 K is equal to 14.715. And so K is equal to, divide that out and you get 490.5. And that's newtons per meter. Okay. So now the natural frequency of the system is 1 over 2 pi times the square root of 490.5 divided by m, which is 1.5. And can someone divide that for me?
I got 2.87 or 2.88.
Okay, 2.88. The units would be 1 over seconds, so this is hertz. So that's 2.88 cycles per second. Okay, so that's oscillating pretty fast.
This clock is terrible.
Yeah, well, it's funny. Well, that probably would be a hard one to use, but
28 point.
good. I'm gonna get to the bottom of this. That feels high. 490.5 divided by 1.5 square root divided by 2 divided by pi. I got 2.88. Okay, so like clocks and stuff, well, clocks actually probably often are set up with the pendulum to be exactly 1 second. But in watches that are getting jostled around all day and stuff, you don't want the thing to take an entire second to oscillate, because when it gets jolted, that oscillation gets interrupted, you know? And so if every time it gets jolted, it messes up a whole measurement of a second, then you're gonna have a lot of error in your calculations. So it's generally felt like if you can overcome problems with friction and whatever, you're better off making it oscillate as fast as possible. Then like one jolt only interrupts 1/5 of a second or 1/8 of a second or whatever, you know? So. And one thing I wanted to say about this is, so notice, you might think that something happens to the frequency when you take this oscillating system and tip it vertically, because then gravity is acting against it, right? it might sort of make sense to you. I think it sort of made sense to me that it would somehow have the effect of stiffening the spring because the spring is stretched farther. But the natural frequency is exactly the same no matter what orientation this system is. Okay. So this is the natural frequency of this spring mass system in any orientation. So if you set it up like this and let it oscillate, or this, or something in between, you can calculate the period and natural frequency of those exactly the same way. It's exactly the same. Okay? I think the problems that I'm going to give you are going to ask you to kind of, they're derivation based. So it's going to ask you to go through this calculation starting with the free body diagram, go into Newton's second law, and go through the calculation that way. Not because it's important for understanding the motion of a specific harmonic system, harmonic oscillator, but because this is an important differential equation that you're going to see in the future in classes, and it's good to wrap your head around it. Okay?
A question.
Yeah.
For the boundary conditions, are there any, you have the general solution and then you have the boundary conditions.
Yeah.
Are there any time where the boundary conditions, I guess, don't set C2?
Yeah, good question. So, yes, you could imagine if you started this thing at time equals 0, this could be at its resting position,
Yeah.
but it could have a velocity, So then what you get is different ratios of cosines and sines. I did the boundary conditions I used were kind of the simplest possible boundary conditions, and it gives you a simple equation of motion that then you can use for the frequency and everything.
So if x dot at 0 was not equal to 0,
right,
then you'd have a ratio.
Exactly. If L was equal to 0 and x dot was equal to something, then you'd only have the sine term. If there was a little of both, you'd have a combination of both of them. But all of those boundary conditions would give you the same natural frequency. Was that your question?
Yeah, so this formula for natural frequency is good no matter what your derivation.
Yes, exactly. Yes. I should write that. So this is... Oh, it always does that at the end of class. Okay. It's also good let's say it's also the same no matter what your boundary conditions are. So let's say no matter what boundary conditions are given. Let me do that real quick. I think I can do this in a minute or two. So let's say we have a general solution x is equal to C1 times the cosine of 20t, so that's our square root of k over m, plus C2 times the sine of 20t. So what's the equation of motion if x at time 0 is 0.02 and x dot at time 0 is equal to negative 0.2. Let's make that something else so you don't get them confused. 0.3. Okay. So x dot let's do x first. So x at 0 is C1 times the cosine of 20 times 0.02, so that is 0.4, right? And plus C2 times the sine of 0.4. No, I'm sorry. I put that in the wrong place. This is at time equals 0, so we have 20, so these are just 0. And so this is equal to 0.02. Okay, this one goes away because sine of 0 is 0. So C1 is equal to 0.02. Okay, and now update that. And we have x as a function of time is equal to 0.02 cosine of 20t plus C2 times the sine of 20t. So now x dot is equal to, this is negative 0.4 sine of 20t plus 20 C2 times the cosine of 20t. So x dot at time equals 0 is negative 0.4 times the sine of 0 plus 20 C2, and that is equal to negative 0.3. I left out my, oh yeah, so this one goes away. And so C2 is equal to negative 0.15. And so our final equation of motion for this would be x as a function of time is equal to 0.02 cosine minus 0.015 sine. But if you're just looking for the natural frequency, the period, that kind of stuff, you get the same thing because it didn't change the argument of the sine and cosine terms. Okay, any questions? All right, that's it.